Hi everyone, today we're talking about Euler paths and Euler circuits. So remember the 7 bridges of Königsberg problem from our last lesson. Pictured here, we have 7 bridges connecting 4 land masses and a graph that we can use to model this problem looks like this, where our vertices are the land masses and the edges of our graph are the bridges that connect those land masses. So the original problem that the people of Königsberg were looking for was a way to cross every bridge once and only once. Last lesson we said that Leonhard Euler in 1735 proved that this was impossible to do on the graph, but why was this impossible to do? So just a definition before we go on, an Euler path is a path that crosses every edge once and only once. So this problem that they were trying to solve now has a name attributed to Euler. An Euler circuit is an Euler path that begins and ends at the same vertex. So those are the same definitions for path and circuit that we saw last class, with the addition that we can cross every edge once and only once. So Euler proved this theorem relating to the degrees of the vertices. So remember, the degree of a vertex is how many edges come into that vertex. So I'm going to write the degrees of these up here. The degree of this one is 3, 3, 3, and 5. Because 5 bridges are coming to meet here, 3 are meeting here, 3 are meeting here, and 3 are meeting at the bottom. So the degrees of each of these vertices is odd. So Euler's theorem says that if a graph has more than 2 odd vertices, there is no Euler path or circuit. It's impossible. And he proved this. We're not going to look at the proof or the method that he used in his original paper, but just know that this is the theorem he developed. If there's more than 2 odd vertices, it will be impossible. So on our model for the Königsberg situation, there are 4 odd vertices, which is why it's impossible. If a graph has no odd vertices, it will have an Euler circuit and therefore an Euler path. And then if a graph has exactly 2 odd vertices, it will have at least one Euler path that starts at one of the odd vertices and ends at the other odd vertex. So in ours above, like we just said, there are 4 odd vertices, thus no Euler path or circuit. So let's look at a few other graphs with the theorem in mind. We want to determine if the following graphs have an Euler path, an Euler circuit, or neither, and then find those if you can. So take a second now and pause your video. Determine if a path or a circuit exists, and then see if you can find it. Another way to think about it, sometimes this problem, this particular one on the left, is presented as, can you draw this without picking up your pen? So pause your video and then start back when you feel like you have an answer for these. Okay, welcome back. So determining if these have Euler paths or Euler circuits, this all hinges on the degrees of the vertices, right? So let's write out the degrees. 2, 1, 2, 3, 4, 4, 1, 2, 3, 4, 4, 2, 4, 1, 2, 3, 4, 4, 1, 2, 3, 4, 4. So on the first graph on the left, all of the vertices are even. There's no odd vertices, so when we're in case 2 of the theorem, therefore this will have an Euler circuit. So we should be able to find a spot to start in that's going to let us cross every edge once and only once. And so you can number or letter, since we've put numbers on the graph already, let's use letters just alphabetically to explain how we're going to travel through this. So let's say we're going to start here, and then we'll cross this edge first, so we'll call it A. Then maybe we'll go here, B, C, D. Maybe what you did is different from what I'm doing. E, F, G, H, I, J, K, L. So following alphabetically, we get A, B, C, D, E, F, G, H, I, J, K, L. Gives us a path that's going to cross each edge once and only once and start and stop at the same place. So that's an Euler path and an Euler circuit. We're going to pick up with these 2 examples in part 2 of the video.